All right, let's get started. Do you have any questions? Okay, so last time we were talking about the, I think the section was 3.2, right? 3.3 rather. Yeah, 3.2. So 3.2, and I want to call it basically linear systems, right, of ODE, of course, with full set of eigenvectors. And the idea is, right, that we have the following equation, okay, the following ODE. And if we say, right, suppose, right, the following lambda I and let's say Vi, okay, are the eigenpairs of A, okay, and let's suppose that here, right, this is an n equation with n unknowns. And so suppose that these are the eigenpairs. We, for now, right, we want lambda to be real because we'll deal with complex eigenvalues soon. But most importantly, right, we want like actually here, right, actually here I from 1 to n. Okay, so by writing this, right, what I mean is that there are n eigenvectors. Okay, there are n eigenvectors. Now, as you saw, right, from our example, when the eigenvalues are distinct, meaning they're all different, then this is guaranteed because each eigenvalue has one eigenvector at least, okay? But when they're repeated, okay, when they're repeated, then it depends on the case. Sometimes repeated eigenvalues have, right, let's say repeat twice, it has two eigenvectors. Sometimes it repeats twice, but it only has one eigenvector. So for those cases, right, we want to look into more details for the ones that don't have enough eigenvectors. But here, right, by writing this, what I mean is it has n eigenvectors for an n by n system. Like a 2 by 2 system has two eigenvectors. So in this case, then the solution, right, the general solution is, right, C1, right, V1, e to a lambda 1, C2, V2, e to a lambda 2, all the way to Cn, Vn, e to lambda n, right? Like that. That's our solution. Okay. Any question on this? So some comments, right? That I think this is, we said that this before, but to emphasize again, these VIs right here are linearly independent. When you found eigenvectors, okay, whether they correspond to the same eigenvalue or they correspond to different eigenvalues, like in this setting, they're always linearly independent. If you found somehow that your eigenvectors are dependent in some way, you made a mistake somewhere, okay? And for that reason, or, you know, for totally kind of like a non-trivial reason, that 0, right, cannot be an eigenvector, okay? So if somehow you're tempted to write down that 0 is your answer for your eigenvector, just don't waste your time because you won't earn any point. No, actually, eigenvectors corresponding to distinct eigenvalues are independent. Actually, when in your statement, right, you have to be careful and say these are two different eigenvectors. Okay, yes, that's true because we don't count, right, you know, different. But if you just pick two eigenvectors corresponding to two different eigenvalues, guaranteed, doesn't matter how you phrase them, they're independent. Again, unless you somehow put a 0 in, but we don't count 0. Yeah. So eigenvectors in general are just independent. You should not find any independent eigenvectors. Okay. So 0, okay, cannot be a choice. Just don't bother. Okay, don't even use it. Won't earn you any point. Okay. All right, so that's where we were last time. We just did a bunch of examples, and that was that. Any question on this before we continue to the next topic? All right, so the next one I want to talk about actually is the geometry, okay, of the solution in this case. So by the way, right, there will be cases, okay, in this chapter, like real eigenvalues, but distinct repeated eigenvalues and complex eigenvalues. For each of these cases, the behavior of the solution is different. So pay attention. I mean, I don't want to keep saying, distinct eigenvalues kind of stuff. So when I say this case, right, obviously I mean the current topic, okay? So actually maybe let me say here, I should go back. Indistinct. I don't even want to repeat eigenvalue here. Distinct non-zero eigenvalue. Okay. Yes, Sagar. No, Sagar. It's 3.2. We didn't get to 3.3 yet. No, when we get there, I'll tell you. Yeah. So, what I want to say here is this, right? That first of all, right, I want to comment on the title of 3.2. Actually, they've talked about straight line solution. Okay, and what that means. So for straight line solutions, right, what does that mean? Notice, right, that let's suppose that we have a 2x2 system. dy dt is a times y. Okay, and let's suppose we have 2x2 system, because here we want to draw a picture. So beyond 2x2 is harder to draw. So what we have, right, is we said that solution is of this form: C1 y1 C1 v1, right, e to lambda 1t plus C2 v2 e to lambda 2t. Okay, and here, right, by my assumption, they're distinct, so they're different. So these two are different. Also non-zero, meaning, right, lambda 1 is not equal to lambda 2, not equal to 0. Okay. So what do I have? Now, what I mean by geometry, right, is the solution curve that we talked about before. So you can call this y1, y2, or you can call it, x and then y, that kind of thing, doesn't matter. Okay. But what do we know, right? So we mentioned this in two different contexts. One is just, what kind of curve can we trace? Another is like, the vector field. All right. So, but they're related. So here, right, what we want to say is this. Look at the solution, right? We say anything like this is a solution. So in particular, right, let's say C2 is 0, then y is C1 v1 e to lambda t, or let's even, right, C1 is a constant, so let's just say it's 1. That doesn't matter. Is a solution for any t. Okay. What does that mean in terms of picture? Well, in terms of picture, right, what it means is you have a vector v1, right, whatever that is, let's say here. By saying that, like, right, this is a solution for any t, right, what that means is that this whole line, right, anywhere it is, right, or actually rather, right, one of the solution, right? One of your solution will be just traveling along this line, right? Going along this line. That's one of the solution. That's one of the possible solution of the equation. Okay. Now, what direction do you travel? Well, suppose V1 is like this, okay? And if lambda 1 is positive, then you travel along the direction of V1. But of course, right, if lambda 1 is negative, then you travel in the opposite direction of V1, okay? But the point is that, right, there is one solution that just basically travel in this straight line as t moves. Yes, it starts somewhere, right? It starts somewhere depending on the initial condition, but it will just move along this line because of this. So similarly, right, there's a V2, right? And again, you just pick this to be 0 and this to be 1. There's a V2. And this V2, right, again, gives another, right, solution that can be entirely based on it. Okay, so there's another solution that's possible that just travels along this straight line. Again, what direction depends on the sign of lambda 2. And also, of course, on where V2 is pointing, okay? So, all right. So this, right, explains why the text, right, 3.2, they call it straight line solutions. They refer to exactly these two straight line solutions coming from, right, the solution that's associated with only one eigenvector, okay? What about the general solution? The general solution, which is this, right, you see is a linear combination of vectors coming from these lines, all right? And that, right, creates all kind of interesting behavior. For example, right, if the arrows, right, on both of these vectors are pointing out, then that means that any linear combination of them will have to point out. Then you have a divergent behavior. Okay. If one of them points out and one of them points in, let's say like this, then you have a behavior that goes in along the V2 but goes out along the V1, for example. If both of them point in, for example, okay, then you have the behavior that like basically going converging like this. Maybe along V1 or along V2, we'll talk about that later. But the point I want to make is that once you have your two straight line solutions, those are like the basis, okay? Those are like the basis vectors. Any other solution right, are constructed as a linear combination of the two straight line solutions. Okay, and what is that? That is just this statement right here, written in English, right? This is the first straight line solution. This is two straight line solutions, right? C1, C2 gives you the mix of how much of the first solution, how much of the second solution you want to combine. All right, and you get all this curvy shape coming out of y1 over x. Oh, what I mean is like, you know, I want to call the first coordinate y1, the second coordinate y2, but let me do this, maybe. Sometimes you call it x. The book call it x, and the second coordinate, they call it y. That's what I mean. It's not over x. Yeah, okay. So it's just a graph of the first coordinate versus the second coordinate. Any question here? So again, right, the message is that the understanding of other solutions come from the understanding of how the two straight line solutions work. Okay, and we'll see the example. All right, right here. So for example, right, let's take a look at this example right here. So yeah, you see, that's why they call it X, they call it Y, right? I like to call my Y1, Y2. But so you see, they say this is the first solution. So 1, 1, right, is their eigenvector corresponding to eigenvalue 4. And here, right, that's this one. And then minus 2, 1, right, is their other eigenvector corresponding to eigenvalue 1. So that's this one. Now, of course, right, actually what one should do also is look at the direction. Is positive here, that means actually direction is this. Is positive here, right? And minus 2, 1, how does that look? Minus 2, 1 points this way, right? So the direction is here. You see? So combining, you try to imagine, right? What I want to say is if you combine the direction, you see that exactly you have that right intuitive movement according to these directions right there, right? If you move like this, so I guess minus 2, 1 here. I wonder why it points downward like this here. Up here is fine, right? Here, 1, 1 is still going this way, but why is it pointing downward? 1 second, 1 second. 1, 1, which is here. So I don't see why the pole is downward like this. Let me think of this a little bit. All right. So this region is a little strange. So I'll think about it. But like what I'm saying is this region, right, from the direction of the movement makes sense. Okay. Let's look at another example. This one. So for this system, right, they claim that there are 2 eigenvectors, right? Where was it? Right here. 1 minus 5 and 1 minus 2. And so the 2 straight line solutions right here. 1 minus 5 and 1 minus 2. Okay. And what are the eigenvalues? Minus 5 and minus 2. So it goes in, right? So it goes in. Oh, I think I know. I'll talk about that a little bit. I'll go back. So what that means, right, is if you look, so for example, 1 minus 5, right? So go to the right 1 and go in 5. So that's this one. So it points this direction. It points the opposite. Okay. And 1 minus 2, right? Go to right 1. And so one of these, right? It points opposite. So basically, what that says is any other combination of these guys will pull you in, you see, for this region. Okay, will pull you in for this region. So let's go back to this picture. My mistake is this. 1, 1, right, is this vector. If I were to look at this, right, if I were to look at this, then the vector will be minus 1, minus 1. Okay, that's also an eigenvector. But if I were to look at this, right, then this is minus 1, minus 1. But remember, right, a multiple of the eigenvector is still eigenvector. So in other words, minus 1 is also an eigenvector, right? The 1, 1 only control this quadrant. If I want to top of this quadrant, right, I want to top of the minus 1, but then the positive eigenvalue, right, says that it points out. So it points out like this. And that's why, right, the direction over here goes like this. Okay. Same thing, right? Minus 2, 1 is this one. And it points out like this. Sorry, right? Point out like this because the eigenvalue is 1. But over here, right, it would be the opposite of that, which is 2 and minus 1, for example. Again, the positive eigenvalue points toward this direction. Okay. So, but the message here is, right, that together with the sign, okay, the sign of the eigenvalue and the direction of the eigenvector, the other behavior is a linear combination, right? It's pull or push, whatever, according to these straight line solutions. Same thing here, right? It's pulled in everywhere. So everywhere that you see is pulled according to the eigenvector. Any question? Okay. So with that, right, actually the topic that we want to talk about is 3.3 now, which is phase portraits of linear system with real eigenvalues. Okay. So that's the title of this section, but right here I think what they're really doing is classification of equilibrium point, and the equilibrium point they're looking at is 0, 0. Okay, so let me explain. The context is still y of t, okay, is dy dt is still a times y, where a is a 2 by 2. We still assume that a has two distinct eigenvalues that are non-zero. Okay. And so what happens is then the solution, as we mentioned, is a combination of two straight line solutions in this language. All right. And we want to, okay, so first of all, right, what is the equilibrium solution in this section or in this example? The equilibrium solution, right, is y equals to 0. Is the only equilibrium solution. Meaning, right, that if you look at the equation a times y equal to 0, right, because you look for dy dt equal to 0, the only solution is y equal to 0 and nothing else. How do we know that? We know that from our assumption that it has two distinct eigenvalues, non-zero. Okay. Remember, if the eigenvalues are non-zero, that's equivalent to the matrix being invertible. The matrix being invertible is equivalent to it only has 0 as a solution to the homogeneous equation. In our context, that implies that 0 is the only equilibrium solution possible. So for the sake of demonstration, okay, let's suppose that V1 is equal to 1, 1, and V2 is minus 1, 1. Okay. You know, like they don't have to be, right? They can be kind of like really close together, like the other example I just gave in the textbook. But here, so y1, y2, right? So I have one straight line solution like this, 1, 1, another straight line solution like this, minus 1, minus 1. Okay. Now, 0 is the only equilibrium solution. In other words, this is the only point that if you start there, you stay there. And this should be like, you know, a strict case, because you remember, like, you know, with our predator-prey example, there could be other, right, equilibrium solutions somewhere here, for example, right? In other words, there could be a balanced position where at this point, the right-hand side is also equal to 0. But because it's a linear, right, system, and A is invertible by assumption, right, such a point does not exist. Of course, exactly, such a point exists when you have a 0 eigenvalue. That's why that case is separated out and discussed, later. So here, right, we only have one single equilibrium solution, which is right here. Okay. Now, so for the first example, right, so we basically have three cases. Sorry. Lambda 1, lambda 2, both positive. Lambda 1, let's say one of them is negative, the other one is positive. So here, maybe let me just write like this, right? Or rather, the product, right, is negative. And the third case is when both of them is negative. Okay. And in each of these cases, what I want to do is I want to classify, right, the nature of the equilibrium solution at the origin. There are three choices for us: sink, source, and saddle. Right? This is like, do I want to call this like the node in the one-dimensional case? I'm not so sure. All right, and we'll explain why these names come from. All right, and how the behavior of the other solutions will be influenced by, right, sink, source, and saddle. Right, basically we're classifying, right? So we want to classify, right, 0, 0. But we also want to discuss the long-term behavior. Asymptotic of the solution. Okay, so quite similar to what we discussed in the one-dimensional case, except that now it's two-dimension and we have to specify into like a very particular class, which is distinct eigenvalues, non-zero. Okay, we'll repeat the same explanation for like complex eigenvalues, repeated eigenvalues, zero eigenvalue, that kind of thing down the road. Any question before we go in and describe these things? All right, so let's look at case 1. Case 1 is when you have both eigenvalues being positive. If both eigenvalues are positive, okay, and suppose that the eigenvectors looks like this, what happens is, like, if you have 1, 1, right, then the solution will go out. If you have -1, -1, then the solution goes out like this. Okay. If you have the other case, is the same thing. Okay. So it's easy to see, right, that if you start anywhere else, because of the influence, right, because of the combination of these two guys, you start anywhere else, you will diverge, you will go away. Okay, so that's why this is called a source. And notice that, right, that when I draw this picture, right, there is a particular direction that the solution. Yeah, Lauren, right? This is where like things get a little bit hairy, so you want to pay attention. The positive part is on the eigenvalue, okay? Not about the eigenvector or solution. So let me demonstrate to you, right? For example, let's just highlight the solution 1, 1. right? And for the sake of simplicity, let's just say lambda 1 equals to 2. So I have this, right? So as t goes to infinity, or as t gets larger and larger, what do we get? We got e to 2t, where both of these values are large. So that's what I'm drawing right here. That's this part. On the other hand, right, this is also a solution for sure. Right, because this is also an eigenvector. And so as t goes to infinity, you got this. So they're both very large, but negative. Okay. And again, right? So yes, we say positive, but what is positive, right? I said it, but it can be quite fast, right? The eigenvalues are positive, and the eigenvalues are the direction of movement along the straight line solution. It's not the sign of the solution. Yes. In fact, right, this solution can get very, very negative because of that. Okay. So 0, 0, right? Let me say again, 0, 0 is a source here. Okay. So the next thing I want to discuss is the asymptotics. Like as this one right here, you mean? Top right, you mean this? Yeah, yeah, like, oh, you know what? It's just my lapse of attention. Yeah, it should go out. It should go out. Yeah. So again, right, I'm not drawing a precise picture, but what I'm trying to do is I'm saying that among the two directions, okay, so basically it's a source. So the solution diverge. Solution diverge. It does not converge as t goes to infinity. All right. So diverge here has a lot of meaning. Okay. But diverge here means it gets larger and larger. Now be careful to not use the language of like going to infinity, that kind of stuff, because right in the plane, right, there's no single infinity for you to refer to, right? Of course, you can make it more precise, but more precise exactly is to point out the asymptotics, okay, meaning the asymptote, where does a solution get close to as t goes infinity. But being a source, right, 0, 0 being a source means that as time goes on, right, wherever you are, you will go away. You will not go to, say, for example, equilibrium as time goes on, right? But yeah, so I want to discuss the asymptotics, like which direction it gets close to. So in other words, I claim that in this case, for example, there is one particular direction it will get close to, and that's a reason for that. Any question here before I explain the asymptotics? So the asymptotics here, right, is this. So it's quite simple. As t goes to infinity, as time goes on, yt, right, the solution will be approximating, or will be closer and closer to the straight line solution with larger eigenvalue. That's it. And I hope that's clear. So for example, right? So in this direction that I'm drawing, right? I kind of point to the 1, 1. So yt will be, right, 1 minus, okay, so I say this, right? C1, 1, 1, let's say e to a 2t plus C2, 1 minus 1, right? E to the, let's say, t. Okay. So as t goes to infinity, right? As t goes to infinity, you see that, sure, right? Both of these guys go to infinity. Both of these guys go to infinity, right? But with the exponential, right? With the exponential, just a slight difference in the exponential, right, can dominate the other terms completely. The other term completely. In other words, right, the term 1 e to 2t, right, dominates term 1 minus 1 e to t. Okay. Uh, how do we want to look at this if we want to make it more precise? Let me try to think. So what I mean by dominate is this, right? If you really have a calculator, you can try. Let's say t equals to 10, okay? You plug in, let's say C1 equal to C2 equals to 1. You plug in for this, okay? And you calculate. Yes, you calculate out. So Lauren, what you will see is that it will be approximately a vector that is like, I don't know, 1,000 something and 1,000 something like this. So what that means is the 1 vector dominates this. That's why for t large, and this is not that large, right? You'll see something that is in the direction of this. Now, let me give you the other example, right? For example, the other example would be, let's say 1 e to a t plus 1 minus 1, let's say e to a 10t. Then if you, again, let's say t equals to 10, C1 equal to C2 equals to 1. Then plug in, you'll see that the vector that you look at is something like 1,000 and minus 1,000. Because now, right, this guy will be dominating. That's what I mean. Okay, but if you do e to 100, I think your calculator might blow up. Who knows? But that's what I mean. Is that okay? There is a way that I can factor out and show you that these terms go to 0, but I have to think a little bit more carefully to show you. But basically, right, when t goes to infinity, this term is much bigger than this term. So when you add them up, you only see this term essentially. Conversely, right, when t goes to infinity, this term is much bigger than this term. So you only see this term essentially. So here, this picture I'm drawing is I'm assuming that lambda 1 is bigger than lambda 2. So the vector will hug the direction of v1. But if the other way happens, then the divergence will happen along the direction of the other eigenvector. Is that okay? Any question here? So to recap, right? The situation when you have two positive eigenvectors, then solution will diverge. 0, 0 is a source. Thus, anywhere you start, you will diverge, but you will be asymptotic to the direction of the eigenvector that has the larger eigenvalue. So those are three characteristics of the behavior of the solution in this case. Okay. Case 2, lambda 1 times lambda 2 negative, right? Let's put it like this. That means one of them is positive and one of them is negative. And so again, right, for the sake of concrete, right? Let me suppose lambda 1 is positive, lambda 2 is negative, okay? Now, so you see, right? Remember, I suppose this is V1, right? This is V2. So lambda 1 being positive, so the solution will come out along the direction of V1. Lambda 2 is negative, so the solution will come in according to the direction of V2. So again, right, this is the 1, 1, and this is the 1 minus 1. Any question here? So in this case, right, the 0, 0 is called a saddle point. Okay. What that means is there's two opposite pole, right? If you are along this guy here, you will diverge. If you're along this guy here, you converge. If you're anywhere else, you will be basically pulled in from along the first guy, yeah. And then you will be, how to say this, right? You will be pushed out along the other guy, like that. And that's why it's a saddle point, or that's why it's called a saddle point. Okay. And so the behavior as t goes to infinity is also clear, right? As t goes to infinity, it will be asymptotic to the guy with the positive eigenvector. Clearly, because the guy with negative eigenvector will disappear right away, right? So as t goes to infinity, asymptotically, yt, right, is close to, or is asymptotic to, is that the right word? I think that's the right word, right? Asymptotic to the solution, right, or to the straight line solution corresponding to lambda positive. Okay. Now, of course, I have had students, right, observing that, of course, if you let t go to negative infinity, right, so you reverse time, then of course you got it to be asymptotic to the solution with negative eigenvalue, which also makes sense because, right, when time goes to negative infinity, then exactly this guy will start dominating, right? So, but again, I only take the point of view that time flows to infinity. So that observation is also correct, but you know, we may not be super interested in it. Any question here? So yeah, but you know, I hope you saw that I cover both cases, right? If it's the other way, then the picture is the same. It just change the direction, right? So yeah, so this is more of the story I'm telling. I'm giving an example like this, but you know, I'll let you figure out the other symmetric case. Okay. So the last one, right, is when both of them are negative. Okay. So first of all, right, along each of this direction, you get pulled in. All right, because both of them are negative. And it's easy to see, right, that in this case, anywhere you are, you will get pulled in. This is easy. This is easy even from the solution because you see y of t is c1 y1, c1 v1 e to lambda 1t plus c2 v2 e to lambda 2t, right? Because both of these guys are negative, then the limit as t goes to infinity, right, e to lambda it is equal to 0. And therefore, right, clearly this will come out to a 0 vector anywhere, right? Any C1, C2, anywhere you start. So that being said, though, right, as the picture I'm drawing suggests, there is a direction, right? It doesn't just come in with any direction. It comes in with a particular direction. And anyone care to guess which direction it is? Right, less negative eigenvalue, or the direction with the eigenvalue that has smaller absolute value. That's right, exactly, right? So as t goes to infinity, right, y of t is asymptotic to the straight line solution corresponding to the eigenvalue that has smaller absolute value. Okay, is this clear? Because, for example, right, if lambda 1, right, in this case, actually, smaller absolute eigenvalue means lambda 1 is bigger than lambda 2. Actually, in this case, I'm drawing the picture of, right, lambda 2 bigger than lambda 1, right? In case you want a concrete number, I'm thinking of lambda 2 is minus 1. This is minus 2, let's say, right? Then, because this is minus 1, for t being really large, right, both of these terms will be super small. But in terms of their smallness, right, the smallness from here will dominate the smallness from here. So you only see this direction. Any question on this? Oh, did I say this is a sink? So in this case, right, 0, 0 is a sink. Yeah. Any question here? So 3 things to remember, right? What is the 3? 2 or 3, I forgot. Anyway, so what is the, okay, maybe 3. What are the signs, right? What are the requirements on the eigenvalues? Well, yes, Carl, but I can see that some complications can get there, right? Because then you have like 8 choices, no? Like plus minus on both. And if they're all minuses, clearly sink, or pluses, clearly source, right? And asymptotic exactly is the same as here. The saddle will be very fun, right? If saddle, then saddle in what sense, right? 1 minus 2 pluses, for example, right? So sure, right? If you understand the idea here, you can say something in the higher dimension. But then how clear you want to describe that, right, is a question, right? But you see, like, for example, all positive and all negative cases, same. But so I suspect, I'm not so sure, again, I'm not an expert in ODE or, rather here dynamical system, that in that case, would people rather prefer to do like 2 by 2, 2 by 2, 2 by 2, like X, Y, Y, Z, X, Z, or rather they want to combine them together? I don't know, right? That depends on the convention and how the field preferred. But yes, concept here applies to the high dimension stuff. Yeah. So right, I mean, the cases, right, for the eigenvalues, remember that, and why, right? What are the straight line solutions look like? Classification on the origin, right, the only equilibrium, and then, right, how does the asymptotic behave? Okay. So let's demonstrate, right, the cases with the examples from the text. So you see, right, that exactly what we describe works here. So here, right, is the first example, which is what? If you look at this, can you see clearly what case it is here? I don't even have to look at a system. I just look at a matrix and I know. What case is this? Exactly, saddle. Why? Because minus 3 and 2, right? And because it's diagonal, right, you see that the 1, 0 and 0, 1 are eigenvectors. And I guess the 1, 0, right, is the one with minus 3, and the 0, 1 is the one with 2, and anything else is a combination of those, right? What about this? So let's see, right? Did I give us the eigenvectors? So yeah, they say, right, V1 is this, V2 is this, and the eigenvalues are minus 3 and 2. Huh. That's also a saddle, right? That's also a saddle. So that's not anything interesting. So this system, right? Lambda 1 is minus 4, lambda 2 is minus 1, so that's a sink. Okay, did they compute the eigenvalues for us? Right, so here, right, the eigenvalues are 1, 1 and minus 2, 1. Which direction would, so it's a sink, right? Which direction would dominate? This or this? As t goes to infinity. Which one is the asymptotic? Yeah, this one, right? So minus 2, 1, the slanted one on this, clearly, see? Okay. Anything else? How about this? This looks like a source, right? Yeah, right, source. Source where this is V1, this is V2. Yeah, Lauren, remember what I said? Here. Asymptotic to the solution corresponding eigenvalue that has smaller absolute value. So here, right, in my example, I let lambda 2 be minus 1. Oh, sorry, right, not smaller, but smaller absolute value, right? Yeah, so lambda 2 is minus 1 or lambda 1 minus 2, right? And in Will's word, it's less negative. I mean, that's perfectly fine if you understand what that means, right? I just want to be more precise. But yeah, right, because this is less negative. So when t goes to infinity, this is much bigger than this, even though, of course, both of them are quite small, okay? Where was I? Okay. So finally, right, this where you see that because both of the eigenvalues are positive, right, they will diverge. It's a source, but which direction does it follow, right? Which direction is it asymptotic to? It should follow the V1, right? Because it's 4, and the V1 is 1, 1. So we expect, right, it follows the line y equals to x. So I think I made a mistake, right? Hold on. So this is the picture. This is a picture. So what was my mistake? Hold on. So I said the asymptotic wrong. It's still that this term should dominate, but sorry. So I need to go back and modify what I said, right? It's actually, it will be parallel to the direction, but it's not exactly asymptotic to this straight line solution. Sorry, how do I want to put that? Okay, so what my mistake was, right, is I say that it looks like this, which is not true, right? Given the picture of the book. What happens is, yeah, because you end up still adding something here that is non-zero. So that's why it cannot be close to this guy. There's a distance between them. The distance being contributed by this term. So what I should say is the direction becomes parallel, okay, which will be correct. The direction will be parallel to the straight line solution. It's not asymptotic to it, okay? I'm not sure what you're saying, Daniel. What do you mean by a single? It's actually a single vector, you see? So basically, it's a single, well, okay, single vector, what does that even mean, right? So it's a single curve, right? Like this curve, or like this curve, or like this curve. It's a single curve, where the curve is described by the combination of these two vectors like this. Is that what you're asking? So, of course, if you combine these two together into one single vector, that's your choice. But yeah, I'm not sure I follow what you're asking. Yeah. But right, but my mistake is this, that right. I mean, the asymptotic works, okay, for the case when both lambdas are negative. The reason is both of them goes to zero. Okay, both of them goes to zero. So that's why it's close to the straight line solution. But the asymptotic does not work exactly when both of them goes to infinity. The reason is this term does not go to zero. So this single one right here, right, will be quite like this. But this gives you a distance. So all I can say is it's parallel to, okay? So let me go back and change that. So will be parallel, okay? Not closer, okay, to the straight line solution. Are we okay? Apologize for the mistake. So actually here you do have an asymptotic as t goes to minus infinity if you care to do that. But again, that's not my interest, right? Because again, I think t goes to the right, right? T goes to infinity, not goes to the left. But right, so there's not quite an asymptotic here if you want to talk about that. But for the other two cases, for the saddle, there is an asymptotic because one of the solution will die away. So it allows you to get close to the other straight line solution. Are we okay here? So yeah, maybe let me change my picture too, right? My picture is misleading. It's not this. It should be, yeah, it should come close to this. It should come out, yeah. And coming close in here, right, exactly is asymptotic as t goes to minus infinity. All right, so this region right here, right, let me maybe choose another picture. This region right here is t goes to minus infinity. And this region right here is t goes to infinity. Is that okay? All right, so for the last 20 minutes, let's continue to discuss 3.4. Oops, wrong color. Complex eigenvalues. All right, so okay, in case you didn't notice, right? So 3.3 is exactly qualitative analysis, right? Because we talk about how, you know, to draw the curve, the asymptotics, the nature of equilibrium solution, that kind of thing. 3.2, right, is analytic solution for real eigenvalues, and so this is analytical approach, right, for complex eigenvalues. So it's probably easier just to look at a example. Let's say dy dt is minus 2, minus 3, 3 minus 2 times y. Okay. So we still follow the approach of finding eigenvalues, eigenvectors. All right. But you will see that the eigenvalues, eigenvectors here are both complex. All right, complex valued. So what is it, right? The characteristic equation is minus 2 minus lambda, right, square. And then minus 9, so plus 9, right, is equal to 0. Okay. So right here, right, you see this says lambda plus 2 square is equal to minus 9. Or lambda, right, is minus 2 plus minus 3i. Is that okay? So now plug in, right? Lambda equals to, let's say, minus 2 minus 3i. Then what we got is 3i minus 3, 3 minus 3i. No, not minus 3i, right? Plus 3i. What's the eigenvector here? What's an eigenvector? Minus 1, 1, I assume you write minus I, right? Somehow the I doesn't show up. Or so I pick I minus 1. How about that? I'll be careful, right, Daniel? I1 won't work because I times I is minus 1. So I minus 1. Okay, yeah, there's this kind of thing that if you, yeah, you may just mess up the sign. Okay, okay, cool. So let me tell you, like, there's a trick. I immediately know for this one that V2 will be minus I1, okay? I'll tell you minus I minus 1. I'll tell you why. It's because there's the observation that complex eigenvectors, eigenpairs, rather come in conjugate pairs. Okay. So first, let me demonstrate to you that this is right, and I'll explain what I mean by this. But so if I plug in, right, as usual, then I got minus 3i, right, minus 3, and then 3 minus 3i, right? So I hope you see that minus i works, right? If I multiply with minus i in here, I got minus 3, right? There are a lot of minuses here, right? The minus cancel with the minus. I times I gives you minus 3, right? Minus 3 plus 3 is 0. So what I said is correct, okay? But there's this nifty rule that, you know, maybe save you a few seconds in calculation, who knows, like this. And so in case you don't know what conjugate means, conjugate is a term in complex numbers that just say this. You conjugate a complex number means you change the negative part to a negative number, to the opposite side, okay? And so first of all, right, notice that, right, the eigenvalues are conjugate pairs, okay? And where does that come from? That comes from, right, this comes from the fact that you always have this kind of expression. Right? If you ever hit on a complex solution, the complex part always comes from this, right? These are all always real because you assume that your quadratic has real coefficient. Therefore, right, the plus minus here exactly just make the conjugation into it. Okay. What about the eigenvector? Okay. What about the eigenvector? Why are they conjugate, right? By the way, right, what do we mean by conjugation of vectors? That means you conjugate each entries. For example, right, let me just do this. Let's say 1 plus I, 1 minus I, right, as a vector. If you conjugate this vector, it becomes 1 minus I, 1 plus I. Okay. And the eigenvector comes from conjugation because something like this. So suppose that lambda v, right, is an eigenpair. Then that means AV is equal to lambda V, right? Now conjugate both sides, then you have this. There's this really nifty property of conjugation that basically says Z1, Z2 conjugate is Z1 conjugate, Z2 conjugate. So what you have here is you can break this down into conjugation part. Right, I don't know, I'm having a hard time conjugate and vector, but like this. Okay, where the A doesn't have any conjugation on it because A is supposed to have real coefficient, like this. But what this reads like is exactly, you know, this is a new pair of eigenpair, vector and the eigenvalue, because this is a new eigenvalue, and this is another eigenvector. And that's why. Okay. Anyway, a detour, you know, on something that maybe saves 2 seconds of your life. But if you don't want, you know, you can always just calculate it out. It doesn't take that long. Okay. So now, what do I do, right? Now I will form solution, right? So first you solve the solution in the naive way, which is this, okay? And I'll do this. So it's I minus 1, right? I minus 1 and minus 2 minus 3i. And I'll do this. I minus 1 e to the minus 3, wait, minus 2, right? Minus 3i times t, okay? All right. And the other is a conjugate of it. So it's going to be minus I minus 1 e to the minus 2 plus 3i times t. Okay. Actually, you know what? So your solution will be like this. First of all, I know what I want to tell you now. Your solution will be like this. This is not acceptable since our solution should be real valued only. Okay. So in other words, what happens is, it's like, say, this is a real system, like a spring mass system, if you will. All right. I can show you the spring mass system actually has complex eigenvalue. But basically, you have a physical system that's real in real life. And say you go through your mathematics and somehow you produce complex solution. You will not have an easy time explaining this to your boss, that whatever that what the meaning of this, because we don't live in a complex value world. Okay. So what do? So you need a way to convert this back to the real solution, right? Real value solution. I think this should be reminiscent of something similar that we discussed, right, in the second order equation. All right, so you need to convert this, right, to real value solution. That's the whole point of this kind of discussion. How would you do this? Okay. Surprisingly, to convert to real value solution, you don't need the second one. You only need one of them. Doesn't matter which one. So in this sense, actually, you don't even need the second part. You don't need this. This is redundant, okay? As I'll explain. You only need one solution. So you work with one solution. Let's say this one. You use Euler formula to transform it into sine, cosine. I have to be careful here, right? There's a minus here. So it should be minus. Right? Be careful here, all right? I mean, this kind of thing can end up hurting you in the end. So here it's really minus with e to minus 2t out. Is that okay? So the minus here comes from the fact that sine of minus 3t is minus sine of 3t, and cosine of minus 3t is cosine of 3t. If you don't want to avoid this kind of confusion, you can always pick the one with a plus, like this one. But of course, right, then you have to pick with the right eigenvector, okay? So if you want. Anyway, okay, so emphasis on this being minus. Then, so this is, right, Euler formula. What you do next is you separate the real and the complex part out, okay? Separate the real and complex part. What does that mean? Well, where is the real component? The real component is, oh, by the way, what am I writing here, right? This is -1. Okay. So the real component, right? So, okay. I guess first let's mix them in. Maybe let's mix them in first before you separate. If you mix them in, right, you can keep the e to minus 2t out, okay? It's a scalar. But if you mix them in, you got minus I times I, right? It's 1. So you got sine 3t, and then plus I cosine of 3t. And the second one gives you minus cosine of 3t plus I sine 3t. Okay. Now you separate to be e to minus 2t sine 3t minus cosine 3t plus I times, let's e to minus 2t cosine 3t sine 3t. All right. So you see one part has an I and one part does not. So that's why I say real complex component. Any question here? So, all right. So again, right, pick one solution, right? Use Euler's formula, combine them, and then separate out the real and complex part. Then surprisingly, this will be your y1, y2. In other words, your solution will be in real value term will be C1 e to minus 2t sine 3t minus cosine 3t plus C2 e to minus 2t cosine 3t sine 3t. That's the solution. Any question? Yeah, okay, I'll get there, right? But does the step make sense? Now, I think that some of you who will not bother to learn this and you want to write down something like this. Yeah, you ignore the I if that's what you're asking, Lauren. Yeah, I'll explain. But yeah, you ignore it. You just take the real portion. But trust me, all right, I don't think you can guess how the sine cosine work, which goes with which, okay? And because it interacts with the eigenvector, right, in a way. So, okay, do follow the procedure. If you somehow guess and got it right, good for you. But right, I think random chance will say that you won't get it right if you just guess randomly. So Will, actually your question is very interesting and is the answer is like this, okay? So the reason is from some statement like this. Suppose, okay, y of t, okay, which is y1 plus I, y2 is a solution to ay, right, equals to y prime, then y1, y2 are both solutions to the same system. Okay, so what I'm saying is like somehow if you can come up with a solution that, okay, so basically what I'm saying is this, right? In shorter version, the real part of solution and the imaginary part of solution are also solutions. That's the term in English, okay? Because, right, this is the real part, this is the imaginary part. Okay, now why is this true? Well, quite simple, right? What does it mean for this to be a solution? Right, that means this works. But how do you differentiate? You differentiate by differentiating the real part and differentiate the imaginary part. So if you plug this structure in here, what you got is y1 prime plus I y2 prime is a y1 plus I a y2. Yes. But you know, there's a famous, right, or there's a very routine trick if you ever deal with complex numbers is if two complex numbers are equal, then you just real must be real, imaginary must be imaginary. So y1 prime solves this, y2 prime solves that. And if they're independent, as you can just observe, then you're good. You have two solutions. Any question? All right, so I think it's a good place to stop here. Okay, we'll pick up on Thursday. Thank you. Thank you. Thank you. You too. Oh yeah, sure. Let me share the screen for you again. You mean around here, Will? Hold on, I don't see your chat anymore. I have to somehow. The reason part. Okay. Yeah. Any question there?